the idea of what a content-based image retrieval system is. And we know that the most important component of CBIR would be how we represent the images and how can we calculate the similarity between different images. So in the following lectures, we will describe several ways to describe images and how to calculate similarity. And one of the most important one is the color information. So here we will introduce color information, how we represent image with color information, and how do we calculate the similarity. And the following material is from this book. It's added. It was added by J.R. Smith. We also see this author from the Visual Seek. He is also the author of Visual Seek system. This table summarizes the features and the distance we will use to measure a content-based image retrieval system. So in the following slide, we will introduce different distance metric that would be based on color histogram or binary set. And these distance metrics belong to different types of distance. And we will evaluate the performance evaluation based on these distance measures. So first of all, we describe the metric properties. So not all functions can be used as a metric. A metric is a dissimilarity or a distance measure that satisfies the following property. The first one is non-negativity. For given two vectors, the distance between these two vectors cannot be negative. So the distance is always larger or equal to 0. The second one is fixity. That means if the distance between two vectors is equal to 0, that can happen only if these two vectors are totally equal. Okay, so only if these two vectors are totally equal, the distance between them can be 0. The third one is symmetricity and symmetry. So the distance between A and B should be equal to the distance between B and A. So this is called symmetry. Also, a metric should follow triangle equality. So the distance between A and B plus the distance between B and C should be larger than the distance between A and C. So this is called a triangle equality. So here may be vector the vector A, here may be vector B, here may be vector C. So the distance between AB and BC, the sum of the distance AB and BC should be larger or equal to the distance between A and C. So for example, the most commonly used distance measure is Euclidean distance. So the Euclidean distance in D-dimensional is defined like this. So the distance between A and B is equal to AK minus BK square, and we take all the square sum and then take the square root. Okay, and we have D real value for each vector. So these vectors are in D-dimensional space. So the commonly used distance matrix is in Minkowski form. So given two vectors, and this vector may represent two color histograms. As we know before, a color histogram can be represented as a vector. So given two vectors or given two color histograms, the Minkowski form distance between these two color histograms can be defined like this. So we can see that we can calculate the difference bin by bin. So calculate the mth bin. So HQm minus HTm. And then we take absolute value and uh, make r square, power square. Okay, r power. Okay, and then we sum all the distance. And the Minkowski form matrix is very commonly used. And actually, Euclidean distance is just one of the spatial case of Minkowski form. Okay, when r is equal to 2, then it would be the square Euclidean distance. But the problem of Minkowski form matrix is that it only accounts for a specific color to the portion of the same color, but not to the proportion of other similar color. So here is an illustration showing this problem. So these are two color histograms, and according to the definition, we see that we only calculate the difference between the beans belonging to the same color range. So we only calculate the distance between these two beans, the distance between these two beans, the distance between these two beans, and sum them together. So the distance between a dark red image and a lighter red image may be the same as the distance as the dark red image and a blue image. So that is the problem, because we don't take the correlation between different colors into account. So this is the problem. This is the problem of Minkowski form matrix. So in the following, we will introduce 8 types of distance matrix and introduce the advantage and the shortage of them. So the first one, D1, is called histogram intersection. Okay. So first, we will normalize the histogram. So if the normalized are not normal, if the histogram are not normalized, then we will take the normalization in the distance matrix. So we can see the normalized version first. So we simply uh, calculate the difference beam by beam and take the absolute value and then sum them together. So this is the so-called also so-called L1 distance. L1 distance. So it's a special case of Minkowski form matrix with R equal to 1, and it's commonly known as a walking distance or city block distance or L1 distance, because this distance definition is equal to the L1 distance. Okay, so we simply uh, take the difference between them beam by beam. And if these two histograms are not normalized, then we simply take the mean of them and then normalize them. So you may wonder what is the mean means. Okay, the minima observation means. So here we can see that given these two histograms, so the first beam may be like this, and then here the first beam may be like this. So this is HQ, this is HT, and this is maybe the second beam. Okay, so if we take minima between them, then actually we take minima between, then we will take this value, and we will take this value, and if we sum all of them, the summation of the minimum between these two histograms is equal to the similarity between these two histograms. So you can imagine that if these two histograms are totally the same, then the minimization, the intersection between them would be the largest, would be equal to 1. Okay, so actually the histogram intersection is kind of concept of similarity. So here we use 1 minus the similarity, so we get the distance. So the distance D1 is a distance measure defined based on histogram intersection, and it's also known as walk distance or city block distance. So D2 is the most commonly used Euclidean distance. We can see the uh, definition here. So now we take square Euclidean distance, and the definition is that this. So we just take the difference between histogram bin by bin and take square, and then sum all this square. And in matrix form or in vector form, we can represent this mass definition like this. So HQ, vector HQ minus vector HT, and take transpose, multiply by HQ minus HT. Okay, so this is the square Euclidean distance. And this formula, this equation can also be decomposed like this. So HQ, so we just multiply HQ by HQ, HT by HT, and then minus HQ multiplied by HT. Okay, and if we normalize the histogram, then the HQ multiplied by HQ is equal to 1 because it is normalized. So this is the HQ is univector. Also, HT is also univector. So the norm, the L2 norm, L2 norm of HT is also equal to 1. So we can simplify this formulation like this: 2 minus 2 multiply HQ transpose HT. So D2 can be derived from inner product of the query HQ and HT. Okay, so conceptually, if the inner product is larger, then the Euclidean distance is smaller. So inner product is kind of concept of similarity. We can also calculate the binary version distance. So assume that we have already represent the color distribution as a binary vector. So just like the color set proposed by J.R. Smith and Professor Shifu Chang before in Visual 6 system, we can represent the color distribution as a binary set. So binary set count the numbers of color with a frequency of occurrence within the image, exceeding a predefined threshold. So we can only if the numbers of pixels is larger than the threshold, then we count it. Okay, we can say that. So a binary set S is an m-dimensional binary vector with the ith entry equal to 1 if the ith entry of the color histogram exceeds t, and it will be equal to 0 otherwise. So binary set indicate the presence of each color, but do not indicate an accurate degree of presence. So if we use binary set representation, the goal is to accelerate the computation, accelerate the similarity computation. So the definition D3 here is kind of Hamming distance. So the definition is like this. So here we minus SQ by ST and take this operation. And this operation denotes the sum of the element of the vector. Okay, the sum of the element equal to 1 of the vector. So this is a kind of Hamming distance. And we can very efficiently calculate such distance. And normalized by the norm of SQ multiplied by ST. So here we can rewrite the definition like this, and the denominator can be very efficiently calculated by the exclusive OR operation. So this is the D3 distance. Distance matrix mentioned above are all Minkowski form matrices, and we know the shortage of such types of matrices. So we can use another type of matrix to complement or to improve the distance matrix. This is the so-called quadratic form matrix. Quadratic form matrix consider the cross relation of the bins. So here is the illustration. In calculating the distance between two vectors, we will also consider the correlation between this bin and all other bins. And we can consider this correlation and take this correlation as a weight to improve the distance matrix. So the quadratic form matrix compare all bins and weight in inter-element distance by pairwise weighting vectors. So the definition, D4, is the so-called histogram quadratic distance measure. And the mathematical definition is like this. The only difference between the quadratic distance and the Minkowski form distance is the matrix A here. We can see that if we eliminate, if we remove the matrix A, it's called HQ minus HT transpose multiply HQ minus HT. So it's equal to the square Euclidean distance. However, now we multiply the matrix A here, and the matrix A, in matrix A, the entries Aij denote the similarity between histogram bins with index I and J. So in naive implementation, the color histogram quadratic distance would be more computational expensive because we have to calculate all the similarity between different colors. So here is the detail of the quadratic distance. So in HQ minus HT transpose, it would be a 1 by n vector like this. Another one, HQ minus HT, would be n by 1 vector. And the matrix A is a n by n matrix. Assume that there are n different bins. So here A11 means the similarity between the first color and the first color. A12 is the similarity between the first color and the second color, and so on. If we have n different colors, this matrix would be an n by n matrix. And by multiplying the vector here by the matrix here, we got another 1 by n vector. And then we multiply this 1 by n vector by this n by 1 vector. And finally, we got a real value. So just repeat this example before why the quadratic distance would be better than the Minkowski form distance. So we repeat this example again. Assume that we only have 3 colors, red, orange, and blue. And if we measure the similarity between these 3 colors, we would get this similarity matrix like this. So we can see that the similarity between red and orange is higher than the similarity between red and blue. Okay, and if we multiply this matrix in distance measure, so we will get the following result. So given a pure red image, we would represent it like this 1, 0, 0, and another pure orange image that would be represented as 0, 1, 0. Then the quadratic distance between x and y, based on this equation, the distance would be 0.2. And if we calculate the Euclidean distance, the Euclidean distance would be square 2, and this is around 1.414. Okay, so we can see that the quadratic distance is largely smaller than the Euclidean distance, and this makes sense because the red image is similar to orange image. Okay, so this would be the effect of quadratic distance. And we can also calculate the quadratic distance based on binary set. So here, the definition of binary set quadratic distance, D5, just like this. SQ minus ST transpose multiplied by the matrix A, and then multiplied by SQ minus st. To further improve the quadratic distance, we can calculate the Mahalanobis distance. Okay, Mahalanobis distance is actually a special case of quadratic form matrix, in which the transform matrix A is given by the covariance matrix, that is A is equal to uh, this one. Okay, and this symbol is often used to represent the covariance matrix. Okay, so this is a special case of quadratic form. Okay, in quadratic form matrix, the matrix A is simply the similarity matrix between different bins, and here the covariance matrix is the matrix A is the covariance value between different bits, different colors. So the idea is that the colors that are widely prevalent across all images are not likely to help in discriminating among different images. Okay, so the idea is like this. So imagine that if in your database uh, many images are tend to be in red, so that the red color or the pink or light red or dark red, the red related colors should not be powerful to discriminate different images, because all images tend to be in red, right? So in this case, if we can consider such variance, then we can build a more accurate, a better transform matrix to improve our distance calculation. Okay, here are some details of the Mahalanobis distance. So given the color histogram descriptor vectors, so let's denote it as x0 to xm minus 1. So there are m bins, there are m color ranges. Then the correlation matrix is given by R, where Rij is equal to the expectation value of xi and xj. In this notation, Ey denotes the expected value of the random variable y. And then the covariance matrix is given by sigma. Sigma ij squared is equal to Rij, the correlation minus by the multiplication of the expectation value of xi and xj. So this is the covariance matrix. And then the Mahalanobis distance between color histogram is obtained if we calculate the distance between SQ and ST. Then the definition would be like this: SQ minus ST transpose. And then we multiply the inverse of the covariance matrix, and then multiply SQ minus ST. And in probability theory and statistics, covariance is a measure of how much two variables change together. So we can illustrate the idea here. So assume that the distribution of xi, s1, and x2 is like this. So if s1 here, s2 here, s1 here, s2 here, and if the s1 and s2 distribution is something like this, we can see that the distribution between s1 and s2 is rather random. That means when the x1 is very large, the x2 would be also very large or also very small. Okay, in this case, the covariance between s1 and x2 is small. And let's see another case. If s1 and s2, the distribution between s1 and s2 is pretty much like this, then we will see that when S1 is larger, S2 is also larger. In this case, the covariance between S1 and S2 would be larger as well. Okay, so the covariance is a measure to show how much two variables change together. So if they often change together, if one get larger, another one also get larger, then the covariance between them would be also larger. Okay. Here is the detailed mathematical definition of covariance matrix. So assume that mu I denote the expect value of the random variable xi, and then sigma ij would be the expectation value of the multiplication between xi minus mu I and xa minus mu j. So we just remove their average value and calculate how they change together, the multiplication between them. Okay, and so this is the whole definition of the covariance matrix. So at the first item, we calculate the covariance between the first variable and the first variable. The second one would be we calculate the covariance between the first variable and the second variable. So this is the whole covariance matrix definition. And why using the covariance matrix is helpful in calculating or to improving the quadratic matrix. So let's go back to the previous slide. Remember that we multiply the inverse of the covariance matrix in the distance matrix. Okay, so here uh, if the covariance matrix value is larger, then the weighting, you can see that the weighting of such distance would be reduced. That means if SQ and ST for some bin, okay, for some color pair, if these two color pair often change together, then the value multiplied here would be smaller, right? So in a word, for the colors that often change together, we will reduce the weight to we will reduce the contribution of the distance between them in calculating the final Manhattan-Mobius distance. So that's the main idea. Okay, if these color pairs often change together, we don't so much trust them. Okay, so we reduce their weight. So this is the main idea of the Manhattan-Mobius distance. And actually, we just consider a special case of Manhattan-Mobius distance. If if different colors are totally uncorrelated, okay, that means the covariance matrix would be a diagonal matrix. Only the value at the diagonal would be larger than 0, and the entries outside the diagonal would be equal to 0. That means different colors are totally uncorrelated. In this case, the Manhattan-Mobius distance would be reduced to this case. And we can see that in this case, this is just a weighted Euclidean distance, right? So if the Euclidean, we can see that the Euclidean distance is simply a simplified version that assumes that all different colors are uncorrelated. Okay, so this is the difference between quadratic distance or Euclidean or Minkowski So this is the main difference between Minkowski-Phong distance and the Mahalanobis distance. Okay. So finally, we often to make performance comparison, we also calculate two very simple color distance. The D7 is defined like this. It's the so-called mean color distance. So we just compute the mean of the color histogram of each color channel. So we just calculate the average red, average green, and average blue to form a vector. And we just calculate the inner product or the Euclidean distance between such simple mean color descriptor to calculate the D7. And if we also consider the color component, we define the distance D8. The color component descriptor based on variance can be represented like this. So we simply calculate the variance, the variance, the variance in the R channel, the variance in the green channel, and the variance in the blue channel to form a variance vector. And then we calculate the distance between variance. So this is the 8 distance measure. To evaluate different distance metrics, here we construct a testbed. We have totally 3,100 color photography, including animal, sports, scenery, people, and so forth. And we take 4 benchmark query, including sunset, flower, nature, and a lion. And we will calculate the relevance score. And the relevance score will be set as 1 if it belongs to the same class as the query image. So we will input a query image, and a few result will be returned. And if a specific return image is belong to the same class as the query image, then it will be given score 1. If it's just partially relevant to the query image, we give it 0.5, and otherwise we give it 0. So a benchmark query is issued to the system, and the system will retrieve the images in rank order. And then for each cutoff value k, the following value will be computed. The so-called cutoff value k is that we only return the top k images that is most similar to the query image. So here we calculate the following value that they actually correspond to true positive, false negative, and true negative. And the definition of all these terms have been introduced before. And then based on these values, we can calculate record, precision, and fall off. So record is the proportion of desired results that are correctly returned. Precision is the efficiency with which the relevant items are returned among the best k. Fall off is actually the false positive rate. Okay, it measures the efficiency of rejecting non-relevant item, and all these terms has been introduced before. So here, let's go through the 4 benchmark query. So the first query is sunset. So here is the query image, and here is the top 4 return image based on the D1 distance metric. Okay, and we can see that most of them are correct. Okay, and here are the return image of the D2 based on D2, based on D3, and based on D4. And we can see that the D3, the return image based on D3 would be not so accurate. Here, you can see that this is the sunflower, not a sunset. Okay, and remember that D3 is what? D3 is the binary, is the Minkowski distance based on binary, based on binary set. And here D5, D6, and D7, D8. And here we can see that the return result of D7 is very bad. Okay, and then remember that what is D7? D7 is if you only represent an image based on average red, average green, and average blue, and then you check the Euclidean distance, then the result would be very, very bad. So don't even try to represent uh, don't even try to represent image based on average red, green, and blue. Don't even try it. Okay, the result would be very bad. And how about represent image as variance? The variance, the result is also bad. Okay, so simple feature would give you bad result. Okay, that's a general guideline. So here is the precision recall curve based on the sunset query. We can see that the precision recall curve, if the curve is close to the right top button, then the performance is better. So here we can see that D1 and D4 is better than D2 and D3, and D6 it seems D6 is the best one. Okay, and we can see that D7 has the worst performance. Okay, so D7 is that we use the average red, green, and blue. So simple feature give us so bad performance. Okay, so here using the mean of each color channel did not sufficiently capture color information in the image. Okay, and the D6 is that we use the Mahalanobis distance. Here is another quantitative performance based on the sunset benchmark query. So here we see that based on different distance metrics, the value here means that the numbers of relevant image in the top 10 or top 20 return result. So if we consider top 10, and based on D1, we have 6 relevant images. Okay, and it's obvious that the value is larger the better. Okay, and if we consider the top 20 return images, 10 of them is relevant to the sunset. Okay, and we can see that the value here D1 is good, D2 is also good, D4 is also satisfactory, but the D7 is quite bad, D8 is quite bad. And if we consider the retrieve to obtain 5 relevant ones, okay, that means in the top 8, we have 5 relevant images until we return the top 8 images. So the value here is smaller the better. So when we return until to the 8 return image, we got the 5 relevant, and we return 20 images, we got 10 relevant. So here the smaller the better. So D1 is good, D2 is also good, D4, and we can see that D7, okay, D6 is also very good. D7, okay, if we return 29 image, we only got 5 relevant. So here the quadratic form matrix D4 and D6 perform well in this query, and the retrieval effectiveness for D1 was slightly better. And this query does not show the quadratic form color histogram matrix improve performance substantially over the Minkowski form. Okay, so here we see similar performance based on D1, D2, D4, D6. The second query is the flower query, and here are the sample result. And we can see that D1 also good, D2 also good, but D3 we can see a bad result from based on D3. And also we got very bad result based on D7 and D8. So here is the quantitative result. So the first row, the larger the better. So we can see that the best one would be D6. Okay, the worst one would be D7. And D1, D2 is also good. And for the second row, we can see the superiority of D6. So the D6 is the best, and then maybe the D1 and D2, and maybe D4. Okay, so D1, D2, D4, D6 are similar in providing good retrieval result. D3 produce a substantial drop. Okay, so remember that D3 is if we use binary set representation, it will cause a substantial performance drop. And the binary set quadratic form D5 improve the retrieval effectiveness over D3. So if we take quadratic form rather than Minkowski form, it can be improved a lot if we only consider binary representation. The third benchmark query is the nature query. So we can see that D1 is also satisfactory, but D2, there is a bad result here. D3, there are several bad results here. D7, quite bad. Okay, and D8, quite bad. So here is the quantitative result. We also see that D1, D2, D4, D6 are good, and very bad based on D7. Okay, and actually the nature query image is the most difficult one because the test set contains many images with blue color that don't come from the blue sky. So we expect to retrieve the image with blue sky. Okay, and the typical queries for unconstrained color photo. The color information provides only a partial filter of semantic content of actual images. And the result of D1, D2, D4, and D6 are similar. And also D3 produce substantial drop, and the D5 improve D3 a lot. And here, this result also tell us that using simple color information may not be good enough to retrieve image. The fourth query benchmark is the lion benchmark, the lion query. So we see that, okay, there's a big, not so good result in D3. We got bad result from D7 and D8. And here is the PR curve based on the lion query image. And we can see that D1, D2, D4, and D6 perform well, and the D7 is the worst. And we can also see this effect based on the quantitative result here. So finally, we found that D1, D2, D4, D6 are excellent. So in summary, D1, D2, D4, D6 are found to be more effective than D3, D5, D6, D7, and D8. And a simple color descriptor D7 and D8 are not effective. And the performance is poor for binary color set. Okay, and D1, D2, D4, D6 are approximately the same. And we also see that simple color features may not be good enough to do very accurate CBIR system. Therefore, we will introduce more visual features in the future.